Good day everyone, and welcome to where we are putting together solutions to the math and science problems that students are getting. In this video, we'll be looking at CSEC Mathematics and specifically the topic of geometric construction. We'll be looking at the past paper's solutions from May 2019 until the present. Feel free to like the video and add any comments down below so we can create other videos to help you in whatever areas that you are struggling. Don't forget to look at the description down below where we have outlined the entire CSEC Maths syllabus in our recommended order for you to get a better grasp of the subject area. If we look at the 10 major topics in CSEC Math, this video looks at topic number 8, Geometry and Trigonometry, which is tested for 8 questions in the multiple choice out of a possible 60 in paper 1, and 2 full questions with 20 marks out of the 100 in paper 2. This topic can be subdivided into 2 parts, into trigonometry and geometry. Geometry itself can be subdivided into 4 parts: geometric construction, unknown angles, circle geometry, which is what this video is about, and the transformation. Let's look at an overview of circle geometry, and there are some basic theorems that we are expected to know. So let's look at the first diagram. In that diagram, we have the 1, 2, 3, 4-sided shape, which is normally known as a dot, and it is formed from the dotted line, from the chord. So from the ends of the chord, we can see that they form an angle at the center and they form an angle at the circumference, and there's a relationship between the two of them. The angle subtended by a chord or made by a chord at the center is twice the angle subtended at the circumference. So if we have x at the circumference, then it's 2x at the center. Now notice one is inside the quadrilateral, inside the shape, and one is outside the shape, the angles. Now, if we take that and we open the legs out even further until it's a straight line, then it moves from being a quadrilateral into a 3-sided shape, a triangle. And the base will be the diameter. So now, if that's given us a straight line, that means 2x is equal to 180 degrees, and therefore x, the angle of the circumference, will be half of that, which is 90 degrees. So what does that tell us? It tells us that if we have a diameter and we form a triangle from it, where of course all 3 vertices are touching the circumference, then this is always a right angle triangle. So it is developed from the dart rule. And if we open the legs even further, then it will go back to being, it will continue being, 2x at the center and x at the circumference. And of course, one angle will be inside the shape and one angle will be outside the shape. Let's look at the 4th diagram. There we can see we have a radius and it's touching a tangent. And what can we see? The tangent to a circle always forms a right angle, which is a 90-degree angle, with the radius. And in our 5th diagram, another radius, and we can see there it is cutting a chord in half, means that it is bisecting it. So when a radius of a circle bisects a chord, the 2 lines form a perpendicular, meaning they form a 90-degree angle between them. And if we go to the next diagram, we see a shape which has 1, 2, 3, 4 sides. So it's a quadrilateral. And all 4 corners lie on the circumference. So it's a special type of quadrilateral. It's called a cyclic quadrilateral. And what relationship can we find within all cyclic quadrilaterals? The opposite angles in a cyclic quadrilateral are supplementary, which means that they will add up to 180 degrees. And if we have two pairs of opposite angles, then we will get 180 plus 180, which will give us 360 degrees, which follows the rules of a quadrilateral as the total interior angles. We can also see that if we extend any one of the sides, then the exterior angle, which is formed by the outside of the cyclic quadrilateral and the side that was extended, is equal to the opposite interior angle. Now let's go to the seventh diagram. And from a chord again, we can see that the chord forms an angle on the circumference in two different places. And what is the relationship between them? The angle subtended by a chord is the same anywhere in that segment, in that part of the circle. In our next diagram, we have a triangle in which all three corners touch the circumference. And if we consider that there's a tangent which meets the circle at one of the corners, then there's a relationship in which we can say the exterior angle between a tangent to a circle and the triangle is equal to the opposite interior angle of the triangle. And in our final rule, we see that we have from a point, it forms two tangents. And we have the radius on both sides, two of them. And of course, from the rule earlier on, the fourth one, we know the angle between the radius and a tangent is 90 degrees. And we have two of those occurring. So we can see in a situation like this, that the tangents, the two of them formed from a point outside the circle, forms a quadrilateral that observes the same rules as a cyclic quadrilateral, which is that the opposite angles are supplementary. So they add up to 180 degrees. And let's look at the general steps that we should follow when we're solving this question. The first being that when you're doing a question, if students are getting problems, then they should make a sketch of these 8 theorems. And then identify which shape is relevant for what is being asked in the question. Redraw that shape, and then apply our rules and solve. May 2019, number 9A, part 1. The diagram below shows a circle where AC is a diameter. Since it's a diameter, let's bring up a blue dot to represent the center of the circle. B and D are 2 points on the circle. So what that means is that if we look at A, B, C, D, it's a four-sided shape, meaning a quadrilateral, and all 4 corners lie on the circumference of the circle. So it's a particular type of four-sided shape called a cyclic quadrilateral. And the DCE is a straight line cutting the circle at 2 points, so it's a chord. Angle CAB is equal to 28 degrees, as shown in the diagram, and angle DBC is equal to 46 degrees, as also shown in the diagram. Calculate the value of each of the following angles. Show detailed working where necessary and give a reason to support your answers. So part 1, we're calculating angle DBA, that small angle there. Now, if we look at the triangle, angle ABC, it has a diameter, and that looks like the second rule there, the only rule with diameter in it. And if we extract it, what do we know? That since it's a diameter, then the angle of the circumference is 90 degrees. So that whole angle at B, angle ABC, is equal to 90 degrees. Let's now extract that, and we know that that whole angle is made up of 2 parts, the angle CBD and the angle DBA will give us the whole angle ABC. So let's substitute. we're going to get 46 degrees plus angle DBA is equal to 90 degrees. So angle DBA is equal to 90 degrees minus 46 degrees, which is equal to 44 degrees. So part 1 is 44 degrees. May 2019, number 9A, part 2. Calculate the value of angle DAC. The chord DC forms the angle DAC, and the chord DC also forms the angle DBC. So this looks like the 7th rule on the right side. And what's the theorem? The angle made or subtended by a chord, which in this case is DC, is the same anywhere in that segment. So angle DAC, the angle at A, is equal to angle DBC, the angle at B, because they originated from the same chord DC, from the same 2 points on the circumference. As such, angle DAC is equal to 46 degrees. May 2019, number 9A, part 3. Calculate the value of angle BCE. And if we look at our shape, angle BCE is the exterior angle of the cyclic quadrilateral. Now let's see if we could look at calculate the angle at DAB, the angle on the inside of the cyclic quadrilateral on the top left. So let's extract it. And what do we know? We know one of the angles is 28 degrees as given, and the other angle is 46 degrees. And where did we get this 46 from? In part 2 of the question, we worked that out. So how do we get the whole angle? Well, angle DAB is equal to angle DAC plus angle CAB. And if we substitute, we're going to get 46 degrees plus 28 degrees, and that's going to give us 74 degrees. So 74 degrees is the entire of that interior angle on the top left of the cyclic quadrilateral. Now, if we're looking at the exterior angle of a cyclic quadrilateral, which rule does that look like? It looks like the 6th rule. And the theorem states in a cyclic quadrilateral, an angle is equal to its opposite exterior angle. So if we extract it, then we can see that the angle on the top left, which works out to be 74 degrees as we just worked out, would be equal to the angle we have bringing up in purple, the exterior of the opposite angle. So angle BCE is equal to angle DAB, and we worked out DAB already, so angle BCE is equal to 74 degrees. May 2021, number 9A, part 1. In the diagram below, E, C, G, and F are points on the circumference of a circle, and these points can be connected by straight lines forming a cyclic quadrilateral. And if we look at the rules on the right-hand side, we can see the 6th rule deals with cyclic quadrilaterals. EG is the diameter of the circle, and if we recognize that and we look at the rules on the right-hand side as well, we can see that the 2nd rule deals with diameter. The tangent AEB is parallel to CD. And if we have a tangent to a circle, then that looks like the 4th rule and 8th rule. Angle AEC is equal to 68 degrees, and angle EFD is equal to 106 degrees. We can also note that there are 2 parallel lines, AB and CD. So much information from the diagram. Determine the value of each of the following angles. Show detailed working where necessary and give a reason to support your answer. Part 1, ECD. So if we look at ECD, we can extract that and recognize that there are 2 parallel lines. And what's the theorem dealing with 2 parallel lines? That those angles, the one we have in red and the one we're bringing up in blue, those are called alternate angles. and alternate angles are equal. So angle ECD is equal to angle AEC. As such, angle ECD is equal to 68 degrees. May 2021, number 9A, part 2. Determine the value of angle CEG. So if we look at that angle, we recognize that there's a diameter with a tangent, which looks like rule number 4. And if we extract that, what do we recognize? That there's a 90 degrees there, because the theorem states the tangent to a circle is perpendicular to its radius or diameter. So angle AEG is equal to 90 degrees. And what do we want to find? We want to find angle CEG. So let's extract that, and notice angle CEG is a part of that 90 degrees. So we can say angle AEC, which we know, and angle CEG, which we want to find, is equal to angle AEG. So let's substitute. 68 degrees plus angle CEG is equal to 90 degrees. So angle CEG is equal to 90 degrees. When we carry the 68 across, it will be minus 68 degrees. So angle CEG is equal to 22 degrees. So we've solved the question. May 2021, number 9A, part 3, find the angle CGF. And if we pull out the parallel lines, let's extract it. Notice we have 106 degrees up on top. So we can find the angle in purple down below, because those two angles together are called interior angles. And that is because the lines AB and CD were parallel. And the theorem states that interior angles are supplementary, which means that if we say angle DFE and angle FEB, the one on top and the one below, we add them up, it will be equal to 180 degrees. And we know angle DFE, let's substitute. 106 degrees plus angle FEB is equal to 180 degrees. So angle FEB is equal to 180 degrees minus 106 degrees, and that gives us 74 degrees. So we're able to find the angle in purple down below. Knowing that now, how does that help us? If we look at rule 8, which shows a triangle and the exterior angle, let's extract it so you can see it better. We know the angle in purple down below, we just got that to be 74 degrees. And the theorem states that the angle subtended by a tangent and the exterior angle of a triangle, which is that 74 degrees here, is equal to the opposite interior angle, which is the angle we have up in red. As such, angle EGF, the one in red, will be equal to whatever the purple angle is, which is 74 degrees. Now that we've gotten that, we can do the same thing for the other side of that angle. So if we extract that again, the angle 68 degrees, which is the angle subtended by the tangent and the exterior angle, that is equal to the opposite interior angle. So up on top in purple will be 68 degrees as well. So angle CGE is equal to 68 degrees as well. Knowing EGF and CGE, let's pull it out together. Then we know the left side and the right side. So the total angle, angle CGF, which is what we want to find, will be angle CGE, the one on the left side, and angle EGF, the one on the right side. Let's substitute that 68 degrees and 74 degrees, which gives us 142 degrees. So angle CGF is a combination of those two smaller angles, is 142 degrees. May 2022, number 9A, part 1. H, J, K, L, and M are points on the circumference of a circle with center O. And out of those 5 points, you can see in the diagram that 4 of those points are connected, and that gives us a cyclic quadrilateral. and the other point is connected to 2 and gives us a triangle. MK is a diameter of the circle and it is parallel to HG, and we see that indicated by the 2 arrows. MJ is equal to JL and angle JMK is equal to 38 degrees. Explain, give me a reason why angle for part A, HJM is equal to 38 degrees. So HJM, take a look at where that is, 2 parallel lines. So let's extract that. And if we look at those lines, we got the 38 degrees and we want to find the angle in black. What can we tell about these 2 angles? Those angles are called alternate angles because they're connected by a transversal and 2 parallel lines. So the theorem states that alternate angles are equal. So angle HJM, the one in black, is equal to angle KMG, the one in red. So angle HJM is equal to 38 degrees. We've proven it. Let's look at angle MJK in part B. Let's extract it. And what can we tell? It looks like the second rule. And the second rule tells us about the fact that the angle subtended at the center, which is 180 degrees, is twice that of the circumference. So angle MJK is equal to angle MOK, the one at the center, divided by 2, which is 180 degrees divided by 2, which is 90 degrees. So we've proven that angle MJK is a right angle. May 2022, number 9A, part 2. Determine the value of each of the following angles. Show detail working where appropriate. So in part A, we are finding angle MLG. Let's see if we could pull out that triangle M, J, and K. And when we take a look at that, we have 2 of the angles. We know 38 degrees and we just found 90 degrees as the angle at J. So if we know 2 of those angles, we can find the third angle. Let's say the angle at M plus J plus the angle at K is equal to 180 degrees. And if we substitute 38 degrees plus 90 degrees plus angle at K is equal to 180 degrees. 128 degrees plus angle at K is equal to 180 degrees. So if we want to find angle K, let's carry it across. So we get 180 degrees minus 128. So the angle at K, which is properly known as angle MKJ, is equal to 52 degrees. Since we have that angle there, MKJ, and we want to find angle MLG, that actually looks like rule number 7 on the right hand side, except it's turned over. And what's the theorem? The angle subtended by a chord, let's extract it, and we have the angle in purple, MKJ, which we just worked out to be 52 degrees, and we want to find angle MLG, the one in black. So the theorem states the angle subtended by a chord, which in this case is JM. So from J and M, we were able to form the angle at K. And from J and M, we can also form the angle at L. So the theorem says that this is the same anywhere in that segment. So angle MLG, which is in black, is equal to angle MKG, which is in purple. And we already worked out the one in purple. So angle MLJ is equal to 52 degrees. As such, we were able to use rule number 7 there to help us to find this angle. May 2022, number 9A, part 2. Determine the value of angle LJK. Now, if we look at angle LJK, it's outside of the triangle. But we know a couple things dealing with that triangle that might help us. So let's extract the triangle. And we recognize that 2 of the lines have indicators on it telling us that they're the same length. So it means it's an isosceles triangle. And the angle at L, which we have in black there, we already know. We found that out in the last part of the question, which was angle MKJ, and that worked out to be 52 degrees. And the angle at L, which is MLJ, and since it's isosceles, the angle in purple is also the same, 52 degrees. So let's see if we can find the angle at G. Since all three angles add up to 180 degrees, angle J plus angle M plus angle L is equal to 180. And angle J plus the other two angles are 52 degrees will give us 180 degrees. So angle J plus 104 degrees is equal to 180. So if we want to find angle J, it's 180 minus 104 degrees. So angle J, which is properly known as angle MJL, is 76 degrees. Now that we've recognized that, let's extract that corner with J on it. And when we extract it, we recognize a couple things. That what we want to find is angle LJK, the one on the outside, right side. But we know the whole angle, MJK, and we know the angle in red, which we just worked out. So angle LJK, which is what we want to find, would be angle MJK, the larger angle, minus angle MJL. And if we substitute, we get 90 minus 76. So angle LJK is 14 degrees. May 2022, number 9A, part 2. The last part of the question. Determine angle JHM. Now, if we look at that, we can see JHM is part of the cyclic quadrilateral. And that rule there, which is number 6 on the right-hand side, indicates to us certain properties. So let's extract it. And what do we recognize? The theorem states that the opposite angles in a cyclic quadrilateral are supplementary, meaning they add up to 180 degrees. So the angle at the angle at H and the angle at K is equal to 180 degrees. And we know the angle at K, MKJ, we worked that out previously, which was 52 degrees. So let's substitute 52 plus the angle at H is equal to 180. So angle at H is equal to 180 minus 52 degrees. So angle H, which is properly known as angle JHM, which is what we want to find, is 128 degrees. So using the cyclic quadrilateral properties, we're able to solve for this. We've now come to the end of CSEC past paper questions in the topic of circle geometry. In our first video in this series, we looked at past paper solutions from May 2009 until 2013. Our second video dealt with past papers from 2014 to 2018. And in this video, we've looked at the solutions from 2019 until the present. Our next video will look at other topic solutions of Maths CSEC. Don't forget to look at the description down below so you can follow the order we suggest in order to cover the entire CSEC Maths syllabus.